After the refreshments, I think we are good to go for the third keynote speech of the day one of ICTer 2017. As the third keynote address, we have Professor S.R. Subramanya. I would like to introduce him before the speech. S.R. Subramanya received his Bachelor of Engineering in Electronic Engineering from Bangalore University, Master of Engineering in ECE from Indian Institute of Science, Master of Science in Computer Science from Indiana University, Bloomington, and PhD in Computer Science from George Washington University, Washington, D.C. He has been the recipient of several awards, including the Richard Merwin Memorial Award at George Washington University and the Grant in Aid of Research Award from Sigma Levin Scientific Society and the Professoriate Award and the Faculty Distinguished Scholarship Award from National University. He is the recipient of a grant from NSF, University of Mysore Research Board, National University System Office of Strategy and Innovation, and from industry. Dr. Subramanya is currently a professor in the School of Engineering and Computing at National University in San Diego, California. He is also the president and the CEO of Xskillsons, pardon for that pronunciation, a company specializing in technical skills enhancement workshops for students as well as for corporate employees. He was formerly a faculty member at the University of Mysore, teaching courses and conducting research in multimedia systems. He has also had working experience at several multinational corporations as a software engineer at Asia AB in Västerås, Sweden, software specialist at Nokia in Helsinki, Finland, and senior research scientist at LG Electronic in San Diego, California. His industry experiences span software for industrial control system, design of software for robot motion planning, and software process improvement in mobile handset software development. He has been a visiting professor at Nayanova University, Russia, Dresden University of Applied Science, Germany, Northwestern Polytechnic University, Xi'an, China, as well as Polytechnic University of Philippines, Manila, Philippines. He is the co-author of over 100 technical papers in referred conferences and journals. He has served as reviewer, program committee member, session chair, and keynote speaker of several international conferences. He has also served as a reviewer for several journals and research grant proposal. He has presented technical tutorials at numerous conferences. He is a senior member of the IEEE. His current research interests are in algorithm design, novel service for digital content, mobile application, and computer science education. So with that introduction, I'm pretty sure that you are looking forward to this interesting session. The today's topic is computational science as a viable mean of solving complex real-world problems. So let me welcome our keynote speaker, Professor S.R. Subramanya. Over to you, sir.
Thank you for the kind introduction. Okay, so this is the title of my presentation. So this is the outline. So I'll just give you a brief introduction of what it is, and I'll go over some typical real-world problems in a variety of areas. and then look at some mathematical models for the solution of several of these problems, and then what a computational scientist should have as a skill set, and then followed by conclusions. So there are many problems in this world, in the scientific world, in engineering world, in manufacturing, in many of these verticals, financial systems, healthcare systems, transportation. The real world problems are very complex. And so we need to understand the problem and then what the issues are, and then come up with some viable solutions. So let me give a simple example. So most of these systems, they can be classified as dynamical systems. So the sorry, I pressed the wrong one probably. Sorry. Okay, I think we are back. Okay. So the dynamical systems is one category of these real world, characteristic of a real world problem. They are very complex systems. They are highly sensitive to the initial conditions. I'll just give two examples. There are many of these, okay? So I read quite some time back about the relationship between insects and humans. I just put it as insects and humans ecosystem. So here is how it goes. Suppose hypothetically, if all the insects were to disappear right now at this moment, they say, this was what I read many years ago. So at that time, I was not thinking about this talk on computational science and other aspects. So I just read it as an informed layperson, this article which appeared, and it seemed so interesting and intriguing and fascinating. So hypothetically, if all the insects on Earth were to disappear at this moment, then through a very complex process of modeling, simulation, and so on and so forth, they concluded that 50 years from now, the human race will vanish. So there will be no human beings on Earth. And then on the flip side, if all the human beings were to vanish from this Earth at this moment, then 50 years from now, maybe 100 years, 1,000 years, maybe million years, everything will continue to survive and thrive. So we have to get a message from this. Now I read it, it was interesting and so on, but now, how do they come up with these kinds of interesting conclusions? They have to have some very interesting model, right? So you can't really make all the insects disappear and then wait for 50 years to see that all human beings disappear. And then one lone person standing will conclude, yes, that was true, and then he will disappear. No. So they have to have some kind of a model. So how do you come up with a model? How do you validate the model? And how do you come up with the conclusions? How do you interpret those? There are so many things here, okay? So this new area called computational science is providing us with some means of doing these things in a cost-effective, time-effective manner, okay? So I'm going to go into some of the details. And probably you might have heard of a term which is used, it's called the butterfly effect. So I saw, as a matter of fact, many years ago, an advertisement on the TV by Honda Motor Company. So at that time, the ad looked very interesting. So I didn't know at that time this was actually referring to the butterfly effect. So what it relates to is the flutter of the wings of some butterflies, say in Brazil, through a chain of events will cause a tornado in, say, Texas. So these are all examples of dynamical systems. So these are very complex systems. And so how do we really model these, simulate these? So that is, I'm going to just give a very high-level overview of these things. So I'm not sure why the animation is not working. So let me just try one more slide. Okay, so it looks like there is a problem with the, although it says here, I know why. Okay, yeah. So, sorry about that. Okay. Okay, so what is computational science? So again, there is no single definition, but most commonly accepted definition is it's a multidisciplinary area which draws upon many techniques from mathematics, computer science, engineering, numerical methods, statistical methods, simulation, visualization, and so on and so forth. So very roughly, you can think of this at the intersection of all these areas like math, CS, computer science, engineering, although I put only these three areas, you can think of intersections of like statistical techniques, data analytics, data science, visualization, and so on and so forth, okay, because it's drawing upon all these different areas. And then it also involves modeling and understanding problems in many different areas like physical sciences, natural sciences, health sciences, social sciences, and so on. And it facilitates the understanding of problems and development of solutions, okay? So obtaining both qualitative and quantitative insights into the complex behavior of these systems. So why computational science? Well, many of these real-world problems are too complex and just to understand. And then problems are complex to be dealt with by pure analytical methods. And experiments in numerous scientific and other domains are highly complex, and they're expensive and they're risky as well. So it is also treated as the third pillar of scientific endeavor and scientific inquiry and scientific discovery. So the two common ones are theory and experimentation, so which has been the norm so far, but now, due to, of course, a lot of technological advancements in hardware, software, mathematical techniques, algorithms, and so on, the third pillar called computational science has become viable, okay? So it enables scientists to solve these complex problems in a cost-effective and time-effective manner. So in many different domains, pretty much all these domains, real-world domains, which are fairly complex, like earth sciences, space exploration, ecology, meteorology, economic forecasting, the microbiological basis of diseases, drug discovery, epidemiology, security, global financial markets, behavior, and so on and so forth. So just to give you a feel for how complex these things are, all those meteorologists have come up with these sophisticated models for weather prediction. So now, of course, it requires a lot of computation. So you can predict the weather on a day-to-day basis fairly accurately. So you can predict rain, you can predict natural disasters like hurricanes, tornadoes, earthquakes, tsunami, fairly accurately in advance. So the recent Hurricane Andrew in Texas, which has caused a lot of havoc, was predicted. So people knew it was coming. So that part, scientists, engineers have gotten to a point where it can be fairly accurately forecast or predicted in advance. So sometime back, even in India, they predicted this hurricane, and then they evacuated all the people in advance, and they saved hundreds of thousands of lives. So that was okay. But what is still too complex is, like in the case of Hurricane Harvey, which hit the Gulf of in Texas, the Houston area, the extent of damage nobody knew. They could only predict. So even today, they're estimating it can be in the tens of billions of dollars. So it's very complex. So our effort should be to get more accurate and improve many of these tasks. So computational science is one of the viable techniques of doing that. So in any of these real world problems, you can call it a system. It could be a financial system, it could be an ecological system, it could be a healthcare system, it could be a transportation system. So I just call it by its generic name system. And then you can do, to understand the system and to make predictions about the system, you can have several means of doing that. So one is doing an experiment with the actual system. Okay, so again, whenever it's possible, whenever it's feasible. So you could do an experiment. The other one is when it's not possible or not feasible, then do an experiment with a model of the system. So model is basically a scaled down version, a simplified version of the real world. And then in the model, you can have either a mathematical model, or you can have a physical model. So a mathematical model, it's only like paper, pencil, computer. Physical model, you have to build the system. You have to build the model of a system which will mimic the actual system in the real world. And then in the mathematical model, you can have an analytical solution if it's fairly well-known, standard, doable, or you can have a simulation. So these are the possible ways to explore an understanding of the system, coming up with a solution to the system. Now, just to give you a, maybe I will allude to this later, but so that I don't lose track and forget, just to give an example of how things have been changing with advances in technologies. Excuse me. So, in the earlier days of aircraft design, so people, of course, did a lot of mathematics, a lot of computations, calculations to come up with the design of the fuselage, design of the wings, rudder, and overall shape of the aircraft, how it's going to withstand all this pressure, drag, and so on and so forth. They still built a model of the aircraft. So it's a physical model they built to scale. And then I'm not sure if you remember, there used to be something called wind tunnels. You have heard of this term, right? So there used to be something called wind tunnels, and then that will simulate the conditions in the real world of the airflow, the turbulence, and many other factors. So this model aircraft was put to test in the wind tunnel, and they observed the behavior, and then they modified the model. This was the physical model. It's a scaled model of the actual aircraft. And then when they were satisfied, then they took the blueprint for manufacture. So that was the way of doing it. So as the modeling techniques, mathematical techniques, algorithmics advanced, and of course the state of the art in high power computing advanced, so they could do a lot of extensive computations in reasonable amount of time. Things change so drastically. So the essential way of doing things has been changing due to these advancements in technologies, mathematics, algorithms, and so on. So nowadays, believe it or not, they don't use these wind tunnels and these actually building a physical model of the aircraft anymore. The very first aircraft which was built without having a physical model was the Boeing Dreamliner, Boeing 777. So they didn't have the wind tunnel, they didn't have the physical model. They completely designed it using computer simulations. So the design and its behavior and response to conditions in the actual, in the real world conditions. So the essence of this is that the computational science is fueled by advances in the core technologies and also some of these techniques, and then that is changing the way things have been done and are going to be done. And so in the next segment, I'm going to give you a feel for some of the real world problems across a variety of areas. So there are far too many, but I've just picked a few here and there. So just to give a feel. Now, simulation of earthquakes Many of these earthquake-prone areas, a lot of researchers are engaged in simulating these earthquakes. So at the Earthquake Research Institute at the University of Tokyo, they are using techniques which can do quantitative predictions of infrastructural damages to buildings, roads, bridges, and so on and so forth. And then also to simulate how the response and recovery mechanisms are there to minimize the damage, death, and injury. Okay, so for this they use, of course, high performance computing together with sophisticated models. And the genetic variations in complex human diseases. So they use, again, extensive computational and statistical tools. The other one is monitoring the air quality and doing aerial reconnaissance, etc., for drones or unmanned aerial vehicles. So there's a model to develop the decision support system for operators. Although it's called unmanned, there are actually a set of people who do the overall control, the finer control, to make better decisions. Okay, so these are all complex real-world problems. So again, understanding the spread of diseases and the cause of diseases. So the viruses causing the West Nile encephalitis, the dengue fever, and yellow fever, and so on. So to understand this, you have to have a model of the dynamics of these infections. Now, just to give you a feel of how these diseases spread, if you take, say, 50 years ago, if there was an outbreak of some disease in some part of the world, it was fairly localized in that part. With the advancements in transportation, so people travel across countries, and the first case where people really, people meaning the scientists studied the outbreak and spread of these diseases was the severe acute respiratory syndrome, SARS. So the SARS, it started somewhere, I believe in some part of China or Hong Kong, I don't remember exactly. But then the spread of the disease was so fast that it was found in many parts of the world. So that was due to, you know, the thinking has to change because of the mobility of the people and many other factors. So there are many things, not just the how the diseases start, but how they spread as well. And then you have to put into place all the mechanisms of the containment of the diseases and further infections and so on. And then in the educational domain, people have been studying. One example is the work done at the HCI, Human-Computer Interaction Institute at Carnegie Mellon. The computer models of student reasoning and learning. So that has been studied and applied for development of educational software and teaching guides. So let me give you a few more, some examples of real-world problems and slowly give you some feel for the complexity of some of these problems and the models that people can come up with. So for drug dosage, so it's not that the physician prescribes some drug with some dosage. So there is actually a little bit of calculation which goes behind that, depending on the age of the person, the weight of the person, and the other drugs the person may be taking, because you have to take into account the drug interactions and so on. So it's a very complex thing, although it looks simple on the face of it. So to determine the prescribed usage of a drug, you have to consider a number of factors, such as the absorption of the drug into the system. When we say system, the human system, essentially, ultimately, it's the blood circulatory system. That's where the drug has to go, and then, of course, reach the organ at the very end. and then the distribution, the metabolism, and elimination. So there's a whole discipline called pharmacokinetics, which deals with all these mechanisms on a quantitative basis. So one of the simplest models that one can think of for the drug metabolism is what is called as the one compartment model. So in the one compartment model, the body is one homogeneous compartment. And then the drug concentration is proportional to the drug dosage. And then you have to find out what the effective dosage is. So there are two limits. So one is called the minimum effective concentration, so below which the drug is not effective. And at the other end of the spectrum is the maximum toxic concentration, beyond which it's going to be dangerous or fatal. So the therapeutic range is between these two limits. And there's also something called drug half-life, which is the time it takes for the half of the amount of drug concentration to be eliminated from the system. So see, you have to take into account all these things. And the concentration and half-life is expressed in relation to the plasma or blood serum. So see, these are many interesting things that I learned while trying to study many of these problems. Like blood has two basic parts. One is the blood plasma, which is the blood cells, and the other is the blood serum, is the transparent liquid which kind of remains after the blood clots. So generally, the human body has about 5 liters of blood. And they say it consists of about, don't add up these two numbers and say, oh, well, 3 plus 3 is not equal to 5. Okay, so the plasma accounts for about 3 liters, and the blood serum accounts for about 3 liters. That's what all these literature tell me. So you have to find out the concentration of the drug and the therapeutic range, or the dosage, and the drug half-life, how much time it takes for 1/2 the concentration to go out of the system. And so that is so you have to make the drug prescription based on many of these factors. Okay, so how do you model this? So we gave a very simple one compartment model where the whole body is treated as one compartment. Well, this is okay if you have, okay, so this is just for the sake of completion, I put this kind of a graphical model. So this is the absorption of aspirin in the blood. Okay, so I'm not going to go into all the details, I'll just, as I said, put for the sake of completion. Now, and a one compartment model is a very simplified model. It's okay for the something like an injection of a drug which goes into the bloodstream directly. Whereas for the case of a pill or a syrup which is taken orally, then you have to think of a more refined model, which is the two compartment model, where the drug gets into the digestive system first. And then in the second stage, it gets into the blood, and then ultimately to the organ targeted by the drug. So this two compartment model is, of course, obviously a little more sophisticated than the one compartment model, and then you have to, there's a lot of mathematics which will go into this, and then so that will determine, so it's like a kind of a reverse engineering. So you have to go backwards, and then you have to prescribe the drug which is going to be much more effective for that particular case or system, which is ultimately the patient. So, and then you have to also model the pumping of the drug from the first compartment, which is the digestive system, to the second compartment, which is the circulatory system. And then people also have come up with multi-compartment models. Okay, so the next problem in the real world is the predator-prey model. So people have studied this for almost 80 years or so, okay? So 80, 90 years. So independently, they were proposed by two scientists, Volterra and Lotka. So this is a very popular model, Lotka-Volterra model, to model the populations of predators and preys. So we'll take a very simple example. So this is prevalent in many different areas as well. So a simple model consisting of hawks hunting the squirrels. Now, we start with an initial population of the hawks and squirrels. And when hawks start hunting the squirrels population goes down, assuming that they are hunted more than the population increase. So when that happens, the squirrel population diminishes significantly, so that leads to a scarcity of food for the hawks. So when that happens, there will be competition among them, and only a few will get the food. The others, which lose out in the competition, will have to starve, and then they die. So that results in starvation for some of the hawks. And the starvation of the hawks will reduce the number of the total population of hawks, which results in, so obviously the hawk population goes down. So the reduced hawk population will give a chance for the squirrels population to grow a little more, because there is less predation. So that increases the squirrel population. So this goes on, and then it will reach some kind of a steady state. So this is the model. As I said, I'm not going to the details of this model. So this is a graphical model. From this, you can derive some kind of an equation. This is a nonlinear equation. This is a differential equation. So the rate, so ds over dt is the rate of change of the squirrel population. And so it consists of two terms. A linear growth based on the current population and the growth rate, and it's the negative term, it's diminished by the rate at which they are predated by the hawks. And the hawk population similarly is modeled, so the rate of change of hawk population is given by dh over dt. And if you plot this over time, starting with some initial populations, you see some kind of a pattern, a repeating pattern. Okay, so as I just described earlier, so the predators will prey on the which are the hawks in this case, on the squirrels, and the population goes down. When it goes down, the predator population goes down, and then when it goes down beyond a certain threshold, the prey population increases, and so on. So people have modeled this, and then you can come up with some kind of a diagram which gives some kind of an equilibrium or steady state situation. So the way to look at this is you start with some initial condition which is here, start with an initial population of the squirrels, which is the prey, and some initial population of the hawks, which are the predators. So you start somewhere here, and then the predators prey on the prey, so and then the prey population will go down until it reaches a point where the prey population is so low that the predators will not get enough food, so there will be competition among them, and then they have to compete fiercely, and only a few can win, and then the others will not get food, so they die of starvation. So this is the decline in the population of the predators, which is shown here in this part. And then it reaches a point after which the prey population starts increasing here, and so on. So it goes on and on. Okay, so that is how several of these things are there in the system, ecological system. So this is a very standard model. However, there are a lot of simplified assumptions here. For instance, the Ks and the constants here, and Kh, it doesn't take into account many factors. For instance, does the number of squirrels preyed upon by a particular hawk, is it the same throughout the cycle, or does it change over time when there is some change in the population and so on, and when there is a competition and so on? So obviously it changes when there is a change in the system characteristic system dynamics. So this model doesn't take into account all these things. So just about 2 weeks ago, I saw an article in a newspaper. There's some people working in India. They published an article, and there was an article in the newspaper about the technical article that they've refined these models. So this is about 90 years old. This came in the 1920s. So people are still working. It's a very complex mechanism. Okay, so the essential idea is to refine this and try to understand the system a little better. See, a model is a simplified view of the real world. It's easy. It's easy to handle, easy to understand, easy to mimic, easy to simulate. But when you go to the complex, when you go to the real world, it's too complex to model. So you have to come up with a particular a point which is optimal in terms of the computations involved, the cost involved, the risk involved, and so on. And of course, the better the model, the more it gets closer to the reality, the better it is, but it comes with a cost. So, okay. So again, advances in all these computational techniques and tools, the core technology, it's pushing the limits of this to understand these things better and better, okay? And enzymatic reactions. So the enzymes are catalysts, so they kind of speed up the chemical reactions for biological systems. So there is something called a substrate. In the presence of an enzyme, it changes to an intermediate enzyme substrate complex, which is called ES, and subsequently the ES undergoes a catalytic reaction, and then it breaks down into an enzyme and a product. So there is a whole area of study called enzyme kinetics, which is the quantitative study of these enzyme behavior. So again, we can model this. There are mathematical approaches to examine the factors which influence the rate of these enzymatic reactions. So this model helps in understanding the causes of many of these metabolic diseases. You might have heard of this model called game of life. I'm just slowly moving from the problem, so I'm also giving you a feel for the model. So there is something called game of life. So this is again a model invented by a mathematician, basically, John Horton Conway at the University of Oxford. It was intended to model the life in a society of organisms. So it consists of a rectangular array of cells, each of which may contain an organism. So each cell has 8 neighbors, except the boundary ones. Oops. So in each generation, births and deaths occur according to following rules. Okay, so an organism is born in an empty cell having exactly 3 neighbors. That's an optimal condition for a new organism to be born. And an organism dies from 2 reasons. One is isolation, the other is overcrowding or overpopulation. So it dies from an isolation if it has fewer than 2 neighbors. And an organism dies from overcrowding, it has more than 3 neighbors. And all other organisms survive. So again, this is a typical example of a dynamical system. So people have studied this extensively. Although it looks very simple, it gives you some very, very interesting results applied in various contexts. Now, the initial conditions are extremely important in determining how the system behaves. So slightly different initial conditions result in totally different outcomes. So this is the basic characteristic of dynamical systems. So people have studied this and they have come up with many interesting behaviors. So let's take another example, which is heat diffusion in a metallic plate. So you have a metallic plate and there is a heat source beneath that. And then, so how does the heat gets distributed? Okay, so this is many different applications in industries as heat shields for rockets, space shuttle, and so on. So how does the heat propagate from a particular point to all the places in the metallic plate? So one of the ways of studying this is to divide the plate into small units called cells or grids, and then start with the place where it's getting heated, and then come up with a simple model which computes the temperature at a particular cell or a grid, which is basically the average of the 4 neighbors. Okay, and then you keep on repeating this, and then that will give you an idea of how the heat propagates in this metal plate. So again, this is a very simple model. So and then what happens when the heat reaches the boundaries? So there is nothing, it cannot go beyond that. So again, it has to be contained within that. And then there are many questions that you can ask. So what is the pattern of this heat distribution? And then when does it reach the steady state? And what will be the steady state temperature? And so on. And the other one is the ball trajectory. So you throw a ball up in the air, and then with some kind of an angular velocity. And then, so what is the trajectory? So at any given point of time, where will the ball be and what will be its velocity? And ultimately, of course, due to gravity, it's going to fall to ground, unless it's the initial velocity is more than what is called the escape velocity. It just escapes the gravity and goes to space. Okay, so these are some of the seemingly simple problems, and you can refine the model and come up with a better understanding of the model and better mimic the real world. And the other example is the biofilms. So biofilm refers to any group of microorganisms in which cells stick to each other and also to a surface. So these organisms could be bacteria or other organisms. Some of the examples are the dental plaque, and it is involved in a wide variety of microbial infections in the body. And also some of these things will grow and will stick and grow on the ship's hulls and water pipes, and even medical devices. So as a matter of fact, people have studied the formation of biofilms on medical devices, and they say 2 million cases of infections occur due to biofilms forming on medical devices. And so that actually they estimate that it's a $5 billion additional healthcare expenses due to this one. So if you can model the growth of these biofilms on these medical devices and then come up with a mechanism of containment of these biofilms, then that leads to quite a bit of savings in the additional healthcare expenses. Okay, so let me give another example of the complexity of some of these. The idea that I'm going to give you is to understand or appreciate the complexity of some of these real world problems. Suppose there's a mission and you have a team of paratroopers. So this is a mission. For instance, there may be some terrorists in a building, and then you need to send these commandos to take them out. So the constraint is that you cannot have a helicopter hovering over the building, because that will give ample, because you have to, all these people have to descend one by one to, via the rope, and then land on the top of the building or the roof, and then so you don't have too much time. And then, of course, the helicopter will be hovering over the building, so that's enough clue for the terrorists inside. So the model is that you have an aircraft which flies high above, so it doesn't have to hover over the building. So it flies over, and then the paratroopers get out of the plane much before the building. So, so the plane flies off, and these people land on the building. So you have to design the time where the people have to get out. So each one have to get out. So the plane will be going at a certain speed, and of course you have the gravity, and you have the building, and you only have so much space on the top of the building, and there is a certain number of people. So you have to model all this and determine exactly at what height the plane should be flying, at what speed, and where these people should be dropped off so that they can land, So you can't land outside the building somewhere else. So it's a fairly complex problem. Okay, so this gives some examples of how this is done. Each person will weigh something, he will be carrying some equipment, and there are some constraints as well. The paratroopers must not be airborne for more than 2 minutes. And of course, they cannot hit the rooftop with a higher velocity because they will be dead. They will crash land. Okay, so and just when I said crash land, I just remembered one very interesting scenario. So let me just give you, these are not in the slides. So in 1999, NASA sent a Mars probe. It's called the rover. So the mission was to send the probe to Mars, which is supposed to land on the Martian surface and grab samples of the soil, analyze that, and send the results back to Earth. So I'm not sure, some of you might know. So this is a multi-million-dollar mistake of unit conversion. So what in the system, in the system they built, the system used was, when they did the calculations, the descent of the craft on the Martian surface was in feet per second. When it was implemented, it was meters per second. So let's say 5 feet per second was the descent rate in their calculations. But when it was actually built, instead of 5 feet per second, it became 5 meters per second because of porting of the software. That's a very, very complex thing. Not complex, it's a very simple thing, but the whole process is complex. So there was a slight oversight. And when they designed, it was 5, this is just an example. So 5 feet per second descent rate, but when it was actually built, the craft was built, it was 5 meters per second. So it was 3 times more than what they thought, and then it crash landed, and it became a piece of junk. So what I'm trying to say is, so in this paragraph, I was just reminded of that when I saw this. They must hit the roof at less than 20 miles per hour speed. Okay, so these things are fairly complex. So we have to model this one. So we have to determine the horizontal distance from the building where the paratroopers must jump off, and the altitude at which they have to open up their parachutes, and then the speed of impact on the rooftop, and the duration they'll be airborne, and so on and so forth. Okay, and of course, the other area is the greenhouse effect and global warming, which has received a lot of attention, which has been receiving a lot of attention, which has received more attention in the past, in the recent past, I would say. So the greenhouse effect in summary is something like this. If you have a car which is parked in the hot sun, the sun, when you just go and park, so everything is fine for now, and then there's no shade, so the sunlight comes through the windows, which is transparent, and then it will try to heat the interior, which is the seat basically, and the other part. So the light is absorbed by the interior of the car, and it is turned into heat, and then it will retain only so much, and then it will dissipate the remaining as infrared back to the environment, which is the air within the car, and then that will not escape to the outside so much, so that's retained. And then the light keeps on coming, and then the heat inside keeps on building up. So this is basically the effect which is happening. This is the model of the greenhouse effect. So there are certain gases which will prevent the heat to escape outside. So these are carbon dioxide, methane, nitrous oxide, etc. So these are called the greenhouse gases. And there are several activities, human activities, which have led to the increase of these. So what does that mean? This means that heat is kind of trapped between the levels of atmosphere and the Earth's surface. Okay, so this keeps on increasing, and people have, in fact, modeled this, and they have also measured many things and come to the conclusion that there has been some increase in the temperature over the years, and it has been shown by evidence also, by breaking of these glaciers in the Arctic regions, and also in the Antarctic region as well, and also in parts of Greenland. So let me wrap it up in the next about 5 minutes. So now, going into the modeling, so there are some major steps in the modeling process. One is analysis of the problem. The second one is the formulation of the model. And so this involves data gathering, making some simplifying assumptions, and determining the variables and the units, and establishing the relationships among the variables and submodels, and determining the equations and functions. So the next step is the model solving. So you have to come up with a solution. So implement the model using some kind of equations and algorithms and dependence on the model, and verifying and interpreting the model solution. And so the next one is reporting on the model and maintaining the model, which is updating the model. Okay? So you can have 6 different categories of models. Let me go over the model classifications, which is, it could be a deterministic model, which doesn't have any kind of chance involved in this. So one example is the model of the movement of these heavenly bodies like Earth, moons, the other planets, and so on. So you can exactly determine where each of these is going to be at a particular point of time. So that's the reason we are able to predict exactly when some eclipse is going to happen, and when exactly this spacecraft taking off is going to land, or the satellite which is launched into orbit is going to be in that place at that exact time. And intergalactic missions, they go millions of miles, they know exactly where the spacecraft is going to be at a particular point of time, and they have to be receiving these signals from millions of miles away, in some cases, of course, in very rare cases, billions of miles away. And there is an aircraft which has gone beyond the solar system, as you know, and still receiving some signals. It's amazing. So these are all deterministic. You know exactly what happens. There's no element of chance. As opposed to that, there is a probabilistic model where there's an element of chance, because you stand at an intersection of 2 roads and a signal, so you don't know exactly when a car passes this intersection. So there's no way of telling that. So, but there are some models. You can say, hey, this arrival rate is like this, and it follows some kind of from very, very interesting, nice probability distributions. So nevertheless, there is an element of chance, so which is a probabilistic or stochastic model. And then you can have a model which is called static. There is no element of time there. And the dynamic model has an element of time. And there are 2 variants in the dynamic model. One is called the discrete model, where the time changes in incremental steps. Okay? And the other one is continuous model, where the time changes continuously. So of course, for simulation, for also to make things easier, some cases, many things happen in the real world continuously. So we model that as a discrete model. Okay? And there are different kinds of, these are the earlier one was different characteristics of the models. The different kinds of models are data-driven models, cellular automaton, agent-based models, matrix models, Markov chains, and graph models. So I started at about 4 o'clock or so. So it's about 4:55. So I'll wrap it up in about 5 minutes. Is that okay? Yeah? Okay. So I'll briefly go over what each one of these is, just to give you a flavor. So in data-driven models, you have the data available, the measurement data is available. So you come up with a nice function which fits the data. So when you do this, you'll be able to make the predictions on points which have not been measured. So it's an approximation, but it depends on how good the measured data is and how good the function fit is for the data. And there are methods of doing that, the regression model and so on. So understand the pattern and find a nice data fit. So it could be a linear function which fits the data, it could be quadratic, exponential, all these, or it could be non-linear, which is complex. So it can be piecewise linear approximation. Okay. So the cell automaton is a 2D array of cells. So each cell has a function. Remember the game of life that kind of gives a very nice, or even the the heat distribution in a metallic plate that fit this kind of a model, the cell or automaton. So each cell has a cell function which depends on the neighbors. So you can have a 4 neighborhood model where it's called the von Neumann neighborhood, or the Moore neighborhood where it has the 4 diagonals as well, which are the 8 neighbors. And then you have to account for the boundary cells and the initial conditions, and then you iterate until you get some kind of a steady state or some kind of convergence. So the agent-based models, each entity is an autonomous decision-making agent. So each agent has a state, a set of state variables and behaviors. So, and this, you know, if you have done some programming in object-oriented, it's nothing different. I mean, these concepts are very similar. So a set of state variables is like the noun, and the behavior is like a verb. There's an action. And there is a method or procedure associated with a class or group of agents. Okay, so and the agents operate in an environment, and the next state is a function of the neighboring agents and the current state of the agent. And so you can also have matrix models where you have many of these traits or characteristics of the system expressed as matrices and vectors, and then you can carry out the standard matrix vector operations. And there are also some well-defined matrices, and also you can have a matrix vector representing a system of linear equations, which have been well studied. So you can apply some of those. And systems having some kind of probabilities of occurrences. So you can have Markov chains or Markov chain model. So you have what are called as states and transitions. And the next state is a function of the current state and the input. And there are probabilities associated with the transition to the next state. So if the system is in a particular state, it can transition to the next state based on the input with a certain probability. Okay? And then the Markov chain refers to a sequence of these variables, basically, starting from some initial condition. It will move to different states. So you call a model a first order Markov model if the value of a variable depends on only just the previous one, or you can call it an nth order if that value depends on the n previous values. And graph models are also very interesting. So a graph basically is a tuple. It consists of a set of vertices and a set of edges, and the edge is could be undirected, directed, weighted, and so on and so forth. And then there are many different kinds of graphs. So it could be an undirected planar bipartite graph. There are numerous properties of graphs, connectedness, colorability, and so on. So many of these real world problems can be nicely modeled as graphs, and there are many algorithms available, pre-packaged, which you can easily apply for the solution of these problems. Okay, now as I said, so I gave you a feel for some of the complexities of the real world problems, and then the kind of high level view of the models. Now I'm going to give you some of the skill set required for a computational scientist, because this is going to be a new, kind of a job scenario for the near future. So the computational scientist should have a good understanding of the emerging technologies, should have a good feel for the societal needs and the nature of technologies, and of course, most important, the ethical issues. And then he or she should be conversant in the development and interpretation of the solutions. And then this is an iterative thing, so keep doing that. And at a finer level, if you go down, the typical skill set consists of understanding the problems from different domains, very quick understanding of the problem, abstraction, problem formulation, and you have to choose the appropriate model for the problem. Okay, you can't force fit some pre-picked model for the problem. And then the choice of the appropriate algorithm and infrastructure, and use of the right simulation technique and tool, and of course interpretation of the results, and then analysis and visualization of data, and then it's an iterative process again. And then you go through the model refinement and then reach a kind of a state where the model is very appropriate, and the solution that you get is satisfactory and feasible and cost effective. So finally, I want to tie this whole thing. So there is a need for a new breed of people called computational scientists for solving many of these real world problems, coming up with better models, coming up with very effective and efficient solutions to real world problems. So there are numerous problems in the real world which need effective and efficient solutions, and there is an industry demand for this. And the computational science courses and programs in the universities are one way of filling these industry demands, so these people graduating from these programs can hit the ground running and then get these solutions in a cost-effective manner, and then so this results in the supply of well-trained professionals. So from the higher education perspective, the institutions need to tackle several of these problems, which is kind of generic problems pertaining to any of these technological disciplines having rapid advancements. So you have to have the curriculum design done properly, and then you have to have the teacher training, who is going to teach those, labs and infrastructure, and frequent updates to the curriculum because they're rapidly changing, and maintain relevance because, again, of the changing needs of the industry and changing problems. For instance, I'll just give one example. In the real world, say 50 years ago, somebody driving on the road and plowing into the pedestrians, like this terrorist activities, was unheard of, right? So the societal problems change. So these days we hear there's a new kind of new dimension to these terrorist activities. So somebody takes a truck and drives through or plows through a crowd. It happened in Germany, it happened in Spain, it happened in Britain. So again, yeah, the reason I'm saying this is you have to maintain relevance. There are new problems coming up, and you have to come up with the appropriate techniques for the solutions and so on. So in conclusion, so there are numerous real-world problems which are far too complex to understand and solve using conventional methods, or which have been existing so far, and experimentation may be prohibitively expensive or dangerous, just not possible. So, and pure analysis is too complex. So the computational science is a feasible, viable method for better understanding and solving complex real-world problems. So this is made possible by faster machines, newer technologies, advances in mathematical techniques, and advances in algorithms. And of course, what do we do in isolation? No, we need courses and programs in higher education to supply these computational science professionals. So with these, I thank you for your time and your attention. Thank you.
Thank you very much, sir. It was very informative, and it seems like anyway we could be a computer scientist or whatever it is, little by little. After all, what we are doing is understanding the nature. So it's what we are actually doing. Anyway, thank you very much for your thoughtful session. And I would like to pay our gratitude with a token of appreciation. So I would like to invite Mr. Kapila Dias. Please be on stage to hand over the plaque. Thank you very much, sir. Okay, so The next item would be the last sessions that we have for the day 1 ICTer 2017. Before we break the agenda for that part, I would like to remind you the conference dinner will be held at the Ozo Hotel starting from 7 p.m. At Valdevattu. So you may find the location through the map, which is already visible at the conference website icter.org. So please be there at the night. And also we are having another session in 3 different places, 3 parallel sessions. So in the second floor, we are having information security session, and on the third floor we are having data analytics session, and here we are having artificial neural network session. So I'll give you 1 minute to pick what you want to listen, and by the time I would like to introduce the session chair for the this session, which is artificial neural network. So I would like to introduce our session chair, Dr. Pradeep Kalansurya. Dr. Pradeep Kalansurya is a doctor of information science and control engineering. His research interests are biosignal processing in virtual environments, applying hologram technologies in virtual learning environment. He obtained his Bachelor of Science degree in Computer Science and Physics from the University of Peradeniya and the Master of Information Technology from the University of Colombo, School of Computing, Sri Lanka. He was a computer programmer in National Savings Bank, Sri Lanka. He obtained Doctor of Engineering of Information Science and Control Engineering from Nagako, University of Technology, Japan. So may I invite our session chair. Here. Okay, I beg your pardon. So there's a mistake. In here, we are having data analytics. And there in the ADMTC, we will be having artificial neural network. So we will convey the same message for all 3 places with the correction. Okay, so let me welcome our session chair, Dr. Pradeep Kalansurya. Over to you, sir.
Yeah, thank you very much for introducing me for this session, and welcome you all for the data analytics session of ICTer 2017. And in this session, there are 3 presenters on the queue, and they will present 2 papers. Without wasting time, I will go into the first presenter. First, Mr. Lahiru Fernando. I will introduce Mr. Lahiru Fernando. Mr. Lahiru Fernando received his BSc degree with honors in computing, specialized software engineering from Stafford University, UK, and MSc from SLIIT Sri Lanka. And in 2011, he joined Pan Asia Bank Corporation as a data analyst and highly involved in developing the data warehouse and BI solutions. and been at Pan Asia